All right, we'll get started in a second. The cat wants. Did I not post the notes already? Yeah, I can post these. I thought I did. Let me check. That was Thursday. th. So many posting of everything. I posted the video and not the notes. I downloaded the notes apparently. They're on Blackboard or they're on YouTube through the link because the previous lecture notes, they'll end up being too large for Blackboard apparently. So they're all on the link in a playlist called Math 115. I'll go there in a second. Just let me upload this. It should be the same links, yeah. Let me stop share this one then, and then I can go to not my daughter's stuff. Where's the share? So yeah, they should be right here. So on there, it should be do full playlist. And then all the videos from the previous classes are up there. And I'll do today and Thursday as well. So yeah, they're all going up on that link. They should be that link. Now let's share this screen again. So yeah, the notes should be up there now. Yeah. So I'll try to have that every day, yes. But as I start doing that, I get emails and stuff like this, and then I start forgetting. But ideally, after class, I'll download the PDF and post it on Blackboard. And then the link that's in Blackboard and on the course outline should just link you right to that playlist. If not, it's just on YouTube under the Tutor Wizard. And then it's the Math 115 playlist. It'll just be the lectures. All right. So last time we were doing logarithms and exponential functions. I'll go over the properties of logarithms again one more time. Then I'll compute a couple examples. I'll remind you what the derivatives are, and then we'll do inverses of the trigonometric functions, and there are the derivatives of trigonometric functions and inverse trig functions. So these are the four main logarithm laws. Addition on the outside of logarithm is multiplication on the inside. Subtraction on the outside is division on the inside. Exponentiation on the inside is multiplication on the outside. And then the last property in particular gave us a nice easy way of computing log base a of x. The log base a of x is natural log x over natural log a. And then so using some of these properties, essentially what we're doing is log is the inverse of exponential. So when we ask what log of 3 is, we're asking what do we raise 12 to get the number 3? And or what are we asking ourselves when we ask log base 12 of 48? We're asking what do we raise 12 to get 48? And these are not nice ones. So what we want to do is combine them usually and get a power of 12 if there's any justice in the world, and I don't have to use a calculator. So log base 12 of 3 plus log base 12 of 48 is going to be log base 12 of 3 times 48 is what we can do. Then we multiply that out. This is going to give me log base 12 of 144. Once I know that, what I'm really asking myself is, what do I raise 12 to get 144? Or you can turn the 144 into a power of 12. As soon as it turns into a power of 12, log base 12 and power 12 cancel each other. So this is log base 12 of 140, or sorry, 144 is 12 squared. And so once that happens, when they touch each other, this cancels, and I get 2. The other way we can do this is log base 12 of 144 equals x if and only if, using the definition of inverse, because this is the inverse, if and only if 12 to the x equals 144. And then you can solve that by saying if and only if 12 to the x equals 12 to the 2. And so I could cancel this way and see that x is equal to 2. Same thing for the second one. We're just going to get a negative exponent this time. I have log base 2 of 6 minus log base 2 of 12. Using the rules, this is log base 2 of 6 over 12. Subtraction on the outside is division on the inside of the logarithms. And now I'm going to make this into log base 2 of 1/2. That's 1/2 is an exponent, -1. So this is log base 2 of 2 to the -1. As soon as the log and its base exponent touch each other, they cancel. And so this is -1. So this is how we're using the logarithm laws to combine and make our life easier. Where's another one? I'll just go on. So basically this is the logarithm laws. And then what did we find out? We wanted the derivatives of each of these. So now we now have the exponential functions. And their inverses, logarithms. Y equals a to the x if and only if log base a of y equals x. This is the definition of inverse. And then we also know, in particular, we now know, in particular, the derivative of these things. The derivative of a to the x is equal to itself times ln a. And in particular, the derivative of e to the x is itself. And then we get the derivative of log base a of x is equal to 1 over x ln a, and then in particular, the derivative of the natural log of x is equal to 1 over x ln e, which is 1. So now we have these new exponential functions and their derivatives. We can also get at the integration of these things, but we'll talk about that when we get to all the categories of integrals, when we start doing this. So the next thing we want are the derivatives of the trigonometric functions. Trigonometric functions and their inverses. And again, we'll focus on sine and cosine and tangent, and then arc tan, arc sine, arc cos, but I'll list them when we first start doing it. I'll list all of the derivatives for completeness. First of all, for the derivatives of the trigonometric functions, we should know what these are already from 114. I'll remind you, but the building blocks are the sine and cosine function. Really, it's just sine x, and cosine x. All other trigonometric functions are defined as ratios of sine and cosine. So to find the derivatives, we have to work hard at this. Therefore, we use the definition to compute the derivative of sine and cosine, and then I use rules to figure out the rest of them. And rules for the rest. What do we mean by this? So what is the derivative of sine x? We use the definition. This is why we get the negative, basically, from trigonometric identities and the definition. The derivative with respect to x of sine x is, by definition, the limit as h approaches 0 of sine of x plus h minus sine x over h. And we use a trigonometric identity, the addition formula. This is equal to the limit as h approaches 0 of sine x cos h plus sine h cos x minus sine x over h. Grouping these together, I have sine x in both, so I can actually take this out. This is sine x times the limit as h approaches 0 of cos h minus 1 over h plus cos x times the limit as h approaches 0 of sine h over h. This is why they want these classic two integrals or limits when they do this in 114 or in the first calculus. They want you to know that this one goes to 0 and this one goes to 1. By the squeeze theorem, we can use L'Hopital's rule in a few weeks or in a couple of days, depending on when we get there. And then what does that give us? That gives us exactly cos x. So the derivative of sine is cos. Similarly, for cos, when you use the double angle formula, you'll get or the addition formula, you'll get a negative in there. That's why the derivative of cos is negative sine. So the moral is the derivative of sine x is cos x, and the derivative of cos x is negative sine x. For all the other ones, we use the quotient rule. and the definition of the reciprocal function. So, for example, tan x equals sine x over cos x. So if I'm going to take the derivative, that says that the derivative of tan x is the derivative with respect to x of a quotient sine x over cos x. So if you really can't remember, just use the basic identities and then the quotient rule. The quotient rule says there should be the bottom, the derivative of the top, minus the top times the derivative of the bottom over the bottom squared. Now when I do that, I get cos squared x, the derivative of sine is cos, and then minus, so we get a plus sine squared x over cos squared x. Sine squared plus cos squared is 1. 1 over cos squared is secant squared. It's good to go through all of these for yourself and see that we're actually just defining or computing the derivatives using the quotient rule and the definition of reciprocal functions. This says the derivative of tan x is secant squared. Similarly, we're going to get the derivative with respect to x of secant x is secant x tan x, which is coincidentally sine over cos squared. When you write these as identities, the derivative with respect to x of cosecant x is negative cosecant x times cotan x, which is coincidentally negative cos over sine squared. And then the derivative with respect to x of cotan x is negative cosecant squared x. So that's the familiar derivatives, hopefully, of the 6 trigonometric functions. They should be fair game. Now we want to do the derivative of the inverses. How are we going to do this? The inverse of trigonometric functions are obtained using the definition of inverse and the implicit differentiation. We don't want to use the definition of derivative, so we want to be clever. So these are calculated using the definition of inverse and implicit differentiation. Which one am I going to do? I can never remember. Sunil usually likes to put some of these as the homework. Which one should I do? I'll do sine, it looks like. Sine x is the one I'm going to do. So if I want to take, if I have, let y equal arc sine x, say, or sine minus 1. I like arc sine. I want to take the derivative of this, but this is if and only if now sine y equals x. And now what I can do is, this is the definition. Now I implicitly differentiate. Now we want to differentiate this equation implicitly. So when I do that, so this is implicit, I'll remind you. When I do this, anything with y, I'm pretending y is a function of x, remember, when I do implicit differentiation. So what do we get? we get the derivative of sine is cosine times the derivative of y with respect to x, and the derivative of x is equal to 1. That immediately tells us that the derivative with respect to y is equal to 1 over cos y. And how do we turn this into an expression of x? Why is this the square root of 1 minus x squared? Well, what we're going to now have is a right triangle. What we have is this definition. We know that sine of y is equal to x over 1, which is opposite over hypotenuse. So this is our angle y. And in that right triangle now, we have that this side is x and the hypotenuse is 1. And so we get the adjacent side using right triangles. We get the adjacent side is 1 minus x squared, square root. And so how do we get this? We now know that we want cos of y is going to be equal to adjacent over hypotenuse, which is equal to the square root of 1 minus x squared over 1. And so secant, or 1 over cos, is equal to 1 over the square root of 1 minus x squared. Therefore, we get our formula. The derivative with respect to x of arc sine x is equal to 1 over the square root of 1 minus x squared. This is where we're getting these. So notice that all I did was, using implicit differentiation, I got the derivative for the inverse arc sine by taking the derivative of sine only. All I did was take the derivative of sine implicitly, and then I cleverly used this triangle to get the derivative of arc sine. In a similar fashion, we can do all the other ones. The derivative of arc cos is equal to negative 1 over the square root of 1 minus x squared. You get a negative in the derivative when you compute that one. The derivative with respect to x of arc tan x is equal to 1 over 1 plus x squared. This one is extremely important for when we do partial fraction decomposition. We need a way of linking that derivative to irreducible quadratic. So note right here, while you have this, because of star, if we integrate, this says that the integral of 1 over 1 plus x squared dx is equal to arc tan x plus c. This will be extremely useful in partial fractions. Decomposition. So that integral right there in particular is extremely important for one of the integral techniques that we're going to get into. We need a way of connecting the integral of an irreducible quadratic in the denominator into knowing that the antiderivative is arctan. Then what we're going to do is split all of our integrals, or all of our rational functions, the denominator, we're going to split them into linear factors and irreducible quadratics, and then make them look like this. And then we can get their antiderivatives as natural logarithms and arctangents. So this will become extremely important later on. For completeness, the derivative of arc, so some blue. The derivative with respect to x of, I'll just write the cotan minus 1x. Willa, you guys can never hear those cats meowing in the background and shit. Really distracting. is equal to -1 over 1 plus x squared. The derivative with respect to x of secant minus 1 is equal to don't do that. 1 over x square root x squared minus 1. And the derivative of cosecant minus 1 is equal to -1 over x square root x squared minus 1. And these ones I don't really memorize either. I just know that if I have to get it, I use the clever definition of inverse, and then I use this implicit differentiation business, and it gets me all of these derivative formulas. So this is the derivative of the 6 inverse trig functions. We will focus on the derivative of sine. Arc sine is 1 over the square root of 1 minus x squared. The derivative of arc cos is -1 over the square root of 1 minus x squared. And the derivative of arc tangent, which is extremely important, is 1 plus 1 over x squared. When we do also that, if we have the derivative with respect to x of sine minus 1 of x is equal to 1 over the square root of 1 minus x squared, then I can integrate both sides. By the fundamental theorem of calculus, it should cancel. So this is the fundamental theorem of calculus part 1. Part 2, sorry. That says the derivative and integral cancel each other. And then therefore, what does this tell us? This tells us immediately that the integral of this radical thing should be sine minus 1. Or we can use trigonometric substitution. And what that's going to get us is x will be sine theta, dx is cos theta, d theta, and then the square root of 1 minus x squared is equal to the square root of 1 minus sine squared x, which is the square root of cos squared x, which is cos x. So this is a segue into one of the other integral techniques we're going to use is trigonometric integrals. Oh, there's one of the cats being bad. Hey, you're bored? They want to go outside in a little while. So now what do? We compute a bunch of derivatives using these guys. Or I can probably go on to and get ahead of the game a little bit, might use the trigonometric functions. But let's do some examples of just computing the derivative. Now that we have these new functions, this is going to be part of the problem. We're just going to keep adding to our lexicon. Now we have these inverse trigonometric functions and inverse log or exponential functions, which we call logarithms. Now we need to know the derivatives of them all. And then when they give you derivatives and L'Hopital's rule of limits and all these types of things, we're going to have to know how to deal with all these new types of transcendental functions. So there's 6 trigonometric functions, 6 inverse trigonometric functions. Now there's 6 derivatives of the 6 trigonometric functions, and there's 6 inverse derivatives. Then there will be 6 integrals of the trigonometric functions, and then 6 integrals of the inverse trig, which we're going to use integration by parts for all the inverses. There's also the exponential functions and the logarithms, and then there's the derivative of the exponential functions and the derivative of the logarithms. Then there's the integral of the exponential functions and the integral of logarithms. And then we get a new category starting probably on Thursday, the hyperbolic functions. So what is this? 1, take the derivative of let f of x equal x arctan or root x. 2, let f of x equal, where did I put e to the x times arc sine 2x plus 1. Let's try some of those. So now all we're doing is taking the derivative. The first thing you want to ask yourself is, we still have to use the chain rule, product rule, quotient rule, all of these rules, but now we have to remember what the derivative of e to the x is and what the derivative of the logarithms are, et cetera, product rule. So for the first one, if I want f prime of x, this is equal to x arctan x to the 1/2, and then I'm taking the derivative. So immediately radicals I turn into their exponents, because I want to use this power rule and quotient rule and product rule, etc. And now I have a product right here. So the last thing that happened was this product. So that should be the first thing I do. When you're taking a derivative, whether there's transcendental functions in there or not, what you're asking yourself is, the first rule I use is the last thing they did to build this. So the last thing they did to build this was they took x and arctan root x and they multiplied them together. That means I'm going to use the product rule. That tells me I'm going to get the derivative of x is 1 times arctan x to the 1/2 plus, I leave x alone, and then I'm going to get the derivative of arctan, which is 1 over 1 plus x to the 1/2 squared times the derivative of the inside, which is 1/2 x to the negative 1/2 by the chain rule. You can leave it like that, or what are we going to get? This will be arctan root x plus, what do we have? We have 1 over 1 plus x times 2. I wish I could move to the front if I'm going to clean this up. And then we have x to the 3/2. The negative 1/2 I can bring to the top, which becomes a positive 1/2, and then I have an x there already. You don't have to clean it up, but there's cleaning it up a little bit. For the second one, we have f prime of x is equal to, again, a product rule, e to the x times arc sine of 2x plus 1. By the product rule, this is the derivative of e is itself plus, leave e alone now and take the derivative of arc sine. There should be 1 over the square root of 1 minus 2x plus 1 squared times 2 by the chain rule. Again, you can leave it like that. You don't have to simplify these things at first. I should say 2x plus 1. So inside, outside function, the product rule, the quotient rule, all of these rules still apply. We just have new functions that we have to take the derivatives of. Yeah, before we do hyperbolic functions, I'll do logarithmic differentiation. So because we know the derivative of logarithms, in particular the natural logarithm, we want to get an entire technique called logarithmic differentiation from this. So using the fact that the derivative with respect to x of the natural log of x is just equal to 1 over x, we can obtain a method of differentiation called logarithmic differentiation. And so when are we going to use this? We will use this for if we have y, which is f of x to the power g of x. So now we're exponentiating one function with another function, or when we want y is a, this is the official way of writing it, a messy or horrible, nasty algebraic function. I'll do both of these. Should I do the nasty algebraic one first? Yeah. I'll define this in general, what we're doing. So it's also based on the logarithm laws. So what we're going to do is, suppose we have y equals f of x to the g of x. I want to take the derivative. And so this does not imply that y prime is equal to g of x, f of x to the g of x minus 1. People want to use the power rule. But the power rule says you have to have x to the a. Or if you had f of x to the a, then you could bring the power down. So it's not the power rule. When you exponentiate one function to another function, you can't just bring the function down and subtract 1. This is not what's happening. Instead, what we're going to do is we're going to use logarithms and implicit differentiation. So instead, what we're going to do is we're going to write y equals f of x to the g of x, if and only if. Now we apply natural logarithms to both sides. And now exponent on the inside becomes number on the outside. This is what we get. Now from this, we implicitly differentiate. Once I do this, so y is a function of x. So what's the derivative of log? 1 over, but then times y prime by the chain rule and implicit differentiation. And then by the product rule and the derivative of log, we're going to get g prime of x times ln f of x plus g of x over f of x times f prime of x by the chain rule. And then now we're solving for y prime. Which is your original function, which is g prime of x times log of f of x plus g of x f prime of x over f of x. Or what they really wanted was, what was y? Y was their original expression, f of x to the g of x. So we get dy dx is equal to f of x to the g of x times this horrible mess, g prime of x natural log of f of x plus g of x f prime of x over f of x. That's essentially the logarithmic formula if you want. I wouldn't memorize these things. I would memorize how we're doing it every time. I want to implicitly differentiate the logarithm after I log both sides and use the power rule. Exponent on the inside is number on the outside, and especially when it's a function, we can get at a formula for computing the derivative a whole lot nicer. So this is the formula basically. How do I want to use this? You could take the derivative of this one just using your rules, product rule, quotient rule, chain rule. But if I have y equals, let's do this one, x squared plus 1, the square root of x plus 2 over x minus 7, some improper rational function. They can get even worse than this. But what I want to do is, same thing, I want to write y equals, or I want to take logarithms of both sides. So the natural log of y is going to equal what? The natural log of this thing, x squared plus 1 times the square root of x plus 1, x plus 2 over x minus 7. Now I start using logarithms. Multiplication on the inside is addition on the outside, and division on the inside is subtraction on the outside. So now this becomes the natural log of y is equal to the natural log of x squared plus 1 plus the natural log of x plus 2 to the 1/2 minus the natural log of x minus 7. Because I want to take the derivative, taking the derivative of this sum now is a whole lot easier than taking the derivative of a product or a quotient. This is why we want to use these logarithm laws. Now what I can do is put that exponent on the outside. This becomes the natural log of y equals natural log of x squared plus 1 plus 1/2 natural log of x plus 2 minus the natural log of x minus 7. Now I can take the derivative implicitly. This says that y prime over y is equal to, I'm taking the derivative now. This will be 1 over x squared plus 1 times 2x by the chain rule, plus 1/2 times 1 over x plus 2 times 1 by the chain rule, minus 1 over x minus 7. And what does that tell me? That tells me that y prime, the derivative I was looking for, is my function. So x squared plus 1 root x plus 2 over x minus 7 times this mess now. So that's one way of computing the derivative without having to worry about the chain rule, product rule, quotient rule a bunch of times. Instead, what they're going to do is just apply logarithms to both sides, use the logarithms to split all the terms up nicely and get rid of all the horrible exponents, etc. Then implicitly differentiate, solve for y prime, put this back in. Yeah. X plus 2 to the 1/2, not x minus 7. It doesn't matter what the exponents are. You could add more exponents if you want. It doesn't even make it that much worse. If you added in an exponent to the 5, then it would just be to the 5, and then you could put a 5 there, and you would get a 5. This is how easy it is to add the exponents. This is why this method, I like this method. Yeah, I copy stuff down wrong all the time, but this is the whole point. Even if you put exponents on the x minus 7, whether it's a 1/2 or any of these other things, what you're going to get is this process makes it a whole lot easier. You don't have to use the product rule or the chain rule and all those types of things. That exponent on the inside now just becomes number on the outside. And so it would just become a 5 like that if I add it in there. So we could add the 5 in or any other exponent. This is the beauty of it. As nasty as these algebraic functions get, the idea is let's apply logarithms to both sides, logarithmic differentiate that, and then just solve for the derivative that I'm looking for. That technique is weird at first, but it's much easier than try it the old way, because you can do this just using the regular rules. Now, example 2 is we're going to use, it doesn't matter which ones we use, but what if I use y is equal to sine, I think one of the homework ones he gives you is x to the x to the x. These are my fault anyways. Can you do the derivative of x to the a to the x, or what about x to the a to the a, or what about x to the a, or x to the x to the a, and what about a to the a to the a, and what about a to the x to the x? Yeah, I had fun with these one day, and I was like, okay, well, we'll take it easy. I think you have a homework one that's x to the x to the x, so let's do the first part. You have to do logarithmic differentiation twice is essentially what you have to do. So let's do this first part. Let's do one, and then I'll do with the other one. Oh, we didn't do sine hyperbolic, so let's do tan minus 1x to the x squared. So solution, what are we going to do for both of these? What we're going to do is we're going to write y equals f of x to the other x. So we have y equals x to the x. If and only if we log both sides, the natural log of y has to equal the natural log of x to the x. Once I get that, what do? The exponent on the inside is what I'm worried about. That exponent becomes number on the outside of the logarithm. So this is if and only if the natural log of y is going to equal x ln x. So once I bring that down, now I implicitly differentiate. Once I do that, the left-hand side is always y prime over y. The left-hand side is always log y. The derivative of log is always 1 over y. And by the chain rule, it's y prime. So the left-hand side is always y prime over y equals, now I use the product rule. The derivative of x is 1, natural log of x, plus leave x alone. And I take the derivative and I get 1 over x, which is 1. So this says y prime equals y times log x plus 1. What was y though? Y equals x to the x. So y prime is equal to x to the x, the log x plus 1. Or the moral of the story is the derivative with respect to x of x to the x is directly proportional to itself, x to the x, and then multiplied by x plus 1, log x plus 1. So if you have to do x to the x to the x, then you have to do this twice. You'll have to do this inside the derivative of the other one. I'll let you try this out. For the second one, I'm going to write y equals, what do we have? Tan minus 1. The x squared. What do we do with this? I log both sides. The exponent comes down. This says natural log of y equals x squared times the natural log of arc tan x. Minus 1 and arc tan are interchangeable. I just write them down when it's convenient for me. Now I implicitly differentiate. It's good to write down on the arrows what I'm doing so that it tells you and it reminds you what we're doing in each step. The left-hand side is always y prime over y. And then the left-hand side should be product rule and the logarithm. So the derivative of x squared is 2x, and I leave that guy alone. Plus x squared times 1 over arc tan x times the derivative of the inside, which is 1 plus x squared. So what does that say? That says y prime is equal to y. What was y? Y was tan minus 1x to the x squared multiplied by this giant hot mess, 2x natural log of tan minus 1 to the x plus x squared over 1 plus x squared arc tan x, or tan minus 1. This is how we compute derivatives using these logarithmic differentiation. Once we have the derivative of logarithms, it's like, okay, well, now I can use this to get, again, nasty algebraic functions, which have a bunch of exponents on them. You can do this the regular way, product rule, quotient rule, chain rule for this guy. Or you can do it with these weird functions, which are raised to another function. And then we can get their derivatives. In particular, this will become useful when we do L'Hopital's rule. Then we'll want limits of these. We're going to do the same type of trick when we do L'Hopital's rule in the exponents. Yes. Arc tan x equals tan minus 1x. Arc sine x is tan minus, or sine minus 1. And arc cos x is cos minus 1x. So it's the same rule. If I have y equals cos x, this is if and only if cos minus 1 of y equals x, or if I have write it as arc cos x, this is if and only if arc, sorry, just trying to write this out. If only if arc cos y equals x. It's the same definition of inverse. It's just a slightly different symbol. I like it because the caution is cos minus 1 of x does not equal 1 over cos x, which is secant x. Secant is the reciprocal. This is inverse. This is the reciprocal. The minus 1 doesn't mean this, but it does mean that in numbers. F minus 1 doesn't mean 1 over f. This is inverse function. This is reciprocal. So in algebraic ones, you can just solve for the algebraic inverse. For these trigonometric functions or these transcendental functions, the whole point is we make them 1 to 1 on a certain interval, or e to the x is always 1 to 1. They pass the horizontal line test. Therefore, they're 1 to 1. Therefore, they have an inverse, but we have no name for it because we can't algebraically solve. So instead of just using the minus 1, this is why in the ones that we use in general, I like to use e to the x, and log, natural log, is the name we gave the inverse of e. And then we have tangent and sine and cosine, and the inverses of those guys I like to call arc tan, arc sine, arc cos, not just minus 1, because it's the specific inverse of these transcendental functions, which is not the reciprocal of these functions. But I digress there, and then I'll post this today. I won't make you wait. I did post the PDF for last Thursday, but I'll post these as well. I'll post all the videos. I'll send out an email for this, but they sent an email saying that we're supposed to be online until February after the break. So yes, this is what I was hoping, and I was sure you were hoping too. We're not going to have to go in particular for the first midterm, or probably, hopefully, both of them. We're going to plan on staying online until after the reading week. And so, yes, I will send an email out about this, but our first exam will not be in class at McEwen. It will be online through CrowdMark, just like the assignments, but I'll send you something when it gets closer. That's next week already, the 24th or something like this. But yes, for your lab quizzes and everything, I would imagine the same thing, but I'll send something out this week. On top of it, Concordia's on strike. Concordia's on strike. I'm teaching at Concordia. So now I have to go back into my lectures on Thursday for them, but we didn't even have lectures last week or this week because they were on strike or something like this. But yes, we will. I will. They just sent us an email saying, I got something, some string stuck to my shirt, but it's the Wild West out there. Everyone's gone rogue. Nobody knows what's going on. None of the instructors, I don't know what's going on either, but they did send me an email saying for sure, no in-class stuff before February, whatever the reading week is. So I would imagine I'm just going to eventually just pull the trigger and say, I don't care what McEwen wants eventually. This is ridiculous. Let's just do it all online and keep it consistent at least. So I plan on keeping everything online unless they really make us do this, because then it makes it easier. One day in class and one day out, and then exams are in class. It seems more confusing. For now, expect everything to be online. All the assignments will be through CrowdMark. All of the midterms will be through CrowdMark. The final exam will be through CrowdMark. If they change this at some point, we might come in class for a couple of things, but otherwise I'm planning on doing everything. Yes, also, I don't know what the link is, but the Learning Center, there's a link. I'll send an email or put this out. You probably should have got this, but there should be, if you go to McEwen's math page, there's a link to the Learning Center. I'm in there Wednesdays from 11 a.m. to 2 p.m. and Saturdays from 11 a.m. to 3 p.m. You can ask anything you want. There's somebody in the Learning Center all day. I think possibly not math all day, but yes, you can ask them about your assignment questions or any other questions you would like. That's fine with me. Yeah. And so I know specifically for me, including on when I say my office hours are, but my office hours are bull crap because half the time I forget to do it and I've just got so many classes and everything else. For sure, I have to be in there Wednesday from 11 a.m. to 2 p.m. and Saturdays from 11 to 3, and it'll be me for sure. And there's usually not that many people there. Like this Saturday, there was 2 people in 4 hours. So it wasn't that bad. It was pretty boring. So yeah, come in there anytime you want and we'll do some math. I'll see you on Thursday.